Hi again, my name's Travis Porter. This is going to be my week 4 video on the Pictures Worth 1,000 Words presentation for Miss Deborah Casey's class for professional communications. So I know that the syllabus suggests that um, we should be picking a topic that is business related. However, I did see that that was preferred and not required. So therefore, I would like to do my presentation on something that I find pretty fascinating, maybe even a little controversial to some people, and that is on the theory of evolution. So Charles Darwin, obviously the founder of the theory of evolution, um, this is the process, the theory of evolution, by which different kinds of living organisms are thought to have developed and diversified from earlier forms of life throughout the history of Earth, right? So that was Charles Darwin's findings and theory of evolution. So one of his strong supporting arguments for this theory is the comparative anatomy. So the comparative anatomy gives evidence to descent with modification, or AKA evolution. Those two terms you can kind of somewhat use interchangeably, right? And so there are, when referring to comparative anatomy, there are three different types of structures. Um, and the first of which are homologous structures, right? So homologous structures are found in organisms that have the same type of anatomy or the same structures, but they have different functions for those structures. So for example, the human arm, right? The structure of it, the bones and things like that, is very, very similar, if not identical in a lot of ways, to that of the wing of a bird, which, reverting that back to the theory of evolution, strongly suggests that we come from one common ancestor throughout deep time, maybe millions and millions of years throughout the earth. The second one is vestigial structures, and those are structures that, as we know it today, serve no purpose for that certain organism. So, for example, the boa constrictor has um, a pelvic bone area in its body, and which suggests that at one time that boa constrictor had legs. But as we know it today, obviously a snake has no use for those legs or does not have legs. So, and the last one is analogous structures, and those structures are pretty much the opposite of homologous structures. And analogous structures are those, um, let's take two different organisms, right, that have a different anatomy, but they have figured a way to use their structures for the same function. So if you look in this picture that we have here, you'll see an insect, like a dragonfly looking creature or organism there, and you'll see a bird. Those are two completely different organisms, but they have developed um, wings that serve the same function, although structurally they are in no way, shape, or form alike. So the theory of evolution as we know it, or as suggested, acts on a population or a species over time. And a lot of people believe that, well, natural selection acts on the individual organism, or this individual species in one relative time, right? So here, and basically natural selection definitively is occurs when organisms with the most successful adaptations leave the most offspring, and therefore the population changes over time to best suit that certain environment, right? So, for example, we see two of the same type of fish here. The fish that is very colorful lives at the top of a waterfall. The fish that is very drab and lacking in color lives at the bottom of a waterfall. So in low predation environments, which is at the top of the waterfall, little to no predation, you'll see that this male fish displays a bright coloration with a larger number of spots. And as opposed to the fish in the high predation area living at the bottom of the waterfall is very drab, suggesting that he wants to camouflage in with his environment with very little spots, right? So this is kind of how natural selection acts on an individual creature, which ultimately over time causes that population to evolve, maybe even into two different types of species here. And lastly, a lot of people believe, well, natural selection, yes, acts on an individual population or an individual, right? But what about genetic drift? So people know genetic drift as, the change in the frequencies of a particular gene or allele due to just chance alone, right? Just genetic drift, it just happens because it happens. So in this example here, the picture at the top of the frogs, let's say, for example, you have three different kinds of frogs. You have red, yellow, green. By chance, just by chance, you lose the three red frogs um, in this small population. By the time you get to the second generation, in theory, you would only have two colors of that frog left. And so in the charts down at the bottom, you'll see that genetic drift can have an effect, whether large or small, and it all depends on the size of the population of the species, right? So in the graph to the right, you'll see that, well, genetic drift in a small population can have a very, very big impact on the population as a whole, maybe even causing variations of that species to become extinct, as opposed to the chart on the right, where this large population of a certain organism, genetic drift as we know it, causes a very small effect on that population just because it's so big. Um, so that's my little presentation on the theory of evolution and a couple of things to do with that. And I hope you've enjoyed it. Thank you.